Hello students, today we will continue with the same topic that was given in the previous session, that is about energy and power uh, in a computer system, the usage of energy and power in a computer system. Especially today we are considering about the usage of power and energy used for microprocessors or the processor that is used as the major element of a computer system. So most of the computer system we are using CMOS chips, integrated circuit chip, as the major element for creating a microprocessor. So CMOS chips are being used for such processor generation. So in these microprocessors, the primary energy consumption is actually because of the switching between transistors. So as you know, an IC actually consists of a number of transistors. So every year, as we were mentioning, every year the designers are actually trying to double or increase the number of transistors present in an integrated circuit. So as we increase the number of transistors, we will be having more switching between transistors. So the major operation that happens within an IC chip is switching between different transistors, switching from one transistor to another transistor. So that is a major element where we require the energy requirement, and for that purpose only we require an overall power also. So that energy is usually called as dynamic energy. So what is dynamic energy? Dynamic energy is the energy consumption that is occurring because of the switching between transistors present in an IC. Okay. So the energy required per transistor. So we are having a number of transistors available in an IC. The energy required per transistor is actually proportional to the product of the capacitive load of each transistor and the square of the voltage, that is voltage square. So we can define an energy, that is dynamic energy, is proportional to the capacitive load present in that particular transistor multiplied by voltage into voltage, that is voltage square. So this is the general definition of a dynamic energy that is being utilized by the transistor present in an integrated circuit. So energy dynamic, that is dynamic energy, is proportional to the capacitive load of that transistor multiplied by voltage square. So this is the equation that is generated by the pulse that is being generated using a complete complete transition, that is usually from 1 to 0, then 0 to 1. So this is the complete transition. So for this entire transition we actually requires the energy equivalent to the capacitive load into voltage square. So this is for a complete transition from 1 to 0 and from 0 to 1. So when we consider for one particular transition, this is for the complete transition. For a single transition, now we will have a modification on the dynamic energy that is already given here, that will be replaced by adding or dividing the same thing by 2. So the energy of a single transition can be defined as half into capacitive load multiplied by voltage square. So dynamic energy for a single transition is proportional to 1 by 2 into capacitive load into voltage square. So that is a variation. So the previous equation was for a complete transition from 1 to 0, 0 to 1, or from 0 to 1, 1 to 0. That complete transition we are having capacity load into voltage square, but in the case of a single transition the dynamic energy is proportional to 1 by 2 into capacitive load into voltage square. Now the power required per transistor is just the product of the energy of a transition multiplied by the frequency of transition. So this is actually dynamic energy. Now what is power? What is dynamic power? What is dynamic power? Which can be defined as I have mentioned in the previous session, energy is actually related to the power. So both these are related. Power and energy both are related. So power, the dynamic power can be defined as, or it is proportional to half into capacity load into voltage square, which is equivalent to the definition of dynamic energy into the number of times the switching happens. The number of times the switching happens within the integrated circuit transistors. So this is for a single transistor, for a single transition, half into capacity load into voltage square. Now for the entire power, dynamic power requirement is proportional to half into capacity load into voltage square into the number of times, or frequency switch, number of times the switching happens. So this is for a single switching, number of times. So what is the total requirement? Now it is converted into the dynamic power. And for a fixed task, slowing the clock rate reduces power. So if the task size is fixed, it's every time we are using the same, or the processor is using the same task. Now if the task is same, we can actually slow the clock rate by that is how we are reducing the power. As you know, if you want to do some work, we require the energy and we require the power. So based on the power only we will be having the energy. This total means the work that is to be completed. So the energy requirement remains the same. The energy requirement remains the same, but if you reduce the clock rate, it will reduce the power requirement. So that is the idea behind the power dynamic, or dynamic power and dynamic energy concept in relation with the transistors present in an integrated circuits. So our aim is to reduce the usage of power and reduce the energy requirement also. So energy is actually tied with a particular task. If the task is fixed, we require the energy for that particular task. The same energy is actually required, but we can reduce the clock rate. So if you reduce the clock rate of a processor, it will actually reduces the usage of power, but total energy requirement for completing the same task remains the same. Now we will see one example, one situation, and we will see the idea of dynamic power. Okay, so in this example it is given like some processors are designed to have adjustable voltage. So one situation is given, some processors today designed to have adjustable voltage, so that a 15% reduction in voltage may result in 15% reduction in frequency also. So if the processor can adjust the voltage, if there is a provision for adjusting the voltage, and if you reduce that voltage into 15%, it may result in 15, we are getting one assumption, it may result in a 15% reduction in the number of times the switching happens, that is the frequency. So automatically if you reduce the voltage, the switching will also be reduced. So that is the assumption we are considering. So in this particular system, so earlier system we are not having the provision of adjusting the voltage. Now the considering system, we are having the provision of reducing the voltage. So as we reduce the voltage, the frequency will also be reduced. So in this situation, so we are having a comparison between an old system and a new system. Old system non-adjustable voltage and current system adjustable voltage. So accordingly we will be having changes in number of frequency switching will also be reduced. So what will be the impact of dynamic power? So that is the question given in this example. So in this example we'll just have a comparison between the old and new processor. So we'll have comparison the new processor to the old system. So as you know, in both situations we are considering the same capacitance. So for the old system and the new system, the capacitance remains unchanged, it remains the same. So now we can have the ratio of power of new system to power of old system. So on top we will write the old new system power formula, and for the bottom part we will write the power formula for the old system. So here as the capacitance remains same for both up and down, so we are not adding that will be means cut off. Both side we are having the same capacitance, so we can reduce we can cut that. Now voltage of the new system is, that is a 15% reduction. That means voltage into, we are only considering 0.85 percentage. So voltage into 0.85 percentage into means square. That is we are only considering 85 percentage of voltage square. So voltage square is part of the power formula into. So we are also having an assumption that the frequency switching will also be reduced to 15%. So frequency switched will also be multiplied with 0.85. So only 85% frequency switching happens. Here also 85% voltage usage, but we are considering voltage square. So as it is 85% voltage into 0.85 square into frequency switched into 0.85. That is the situation of a new system. So this is the situation of a new system. Now what we are considering for the old system, here we are considering voltage square, that is a normal formula, voltage square into frequency switched. There was a capacitance here, capacitance load. Here also we are having capacitance load. We are considering the same load for both new and old system, so both will be cut down. So now this is the formula we are having. So totally after considering these 2 points, what we are actually getting, so frequency switched will be cut off, voltage square will also be cut off, 0.85 square into 0.85, that is 0.85 cube is equivalent to 0.61. That is the power requirement for a new system. So this is power new to the old system. Power new, this is the ratio we are getting, power new to the old system. This is power new, this is power old. We are getting 0.61. So what is the conclusion? We are actually reducing the power requirement to 60%. So if the old system is requiring 1, means the power requirement is 1, the new system requires only 0.61 power percentage only, 0.61% only power is required for the new system. So what is the assumption we are taking? The new system is having adjustable voltage and that is reduced to 15%. So automatically 0.85 voltage square, and accordingly we are having reduction in number of frequency, number of times the switching happens, that will also be reduced to 85%. That means reduced to 15%, and we are having only 85% frequency switching happens. Okay, so 0.85 square into 0.85, 0.85 cube, 0.61. Only 60% of power is being utilized for the new system when compared to the old system that use the entire 100% of power. Okay, so if you are having a multiprocessor, if you are having a processor with adjustable voltage, and if you adjust the voltage or that is being reduced, automatically the frequency will also be reduced, and because of that the new system, so this is from the designer point of view. So here he is thinking about designing a system with with less power requirement. So we are actually getting a lower power, we actually require a low power for the new system that is being created based on this situation. Okay, so this is just an example for considering the power requirement of a new system. We are considering a new system with new power requirement in comparison with an old system with the 100% of power requirement. Okay, so we can see the difference between these two. if we cannot do the voltage adjustment, it remains the same. Early system also require 100%, new system also will be requiring 100% of power, but we can actually reduce that power requirement in this scenario. So we are simply substituting our previous formula for the new system as well as the old system for finding out the power requirement of a new system. I hope it is clear. Now we are considering about the different techniques to improve the efficiency of energy efficiency despite flat clock rates and constant power supply. So we are assuming that we are having flat clock rates, so a normal clock rates will be maintained, and as well as we are having a constant power supply being applied to the we are assuming that situation. So what are the different solutions? Some processor, when the architecture, the designer tries to develop a new system, he need to consider how we can save the power, how we can have a system with less power usage, and how we can have a system with less energy consumption. Okay, so that is the consideration. So we are assuming that we are having the normal flat clock rates available. Clock rate decides the speed of the system, and the power supply also we are assuming that all the processor requires the same constant power supply. So what are the different solutions for improving the efficient energy usage of that particular processor? So we are considering about generally we are considering about different microprocessors, so it may vary in different processes, but we are considering the general methods. We are having 4 methods available. 3 methods are given in this slide, and the last one is given in the next slide. So first point is given like do nothing well, means we don't need to do anything extra. So what it can do is turn off all the clocks of the inactive modules. So how we are saving the power usage in our home? If we are watching TV, we will be sitting in the room where TV is placed, and we don't need to switch on all the power supplies, all the bulbs and all the devices, fan and other devices present in other rooms. What we are doing, we will switch off all the inactive areas, right? Similarly, for the computer system also, if only one portion is working, only for that portion the clock need to be active. See what is happening, turn off the clocks of inactive modules to save energy. Okay, so if some other area in the processor, some area it is actually active and the remaining area is not active, means just switch off or turn off the clock of that particular. If the power requirement is actually decided by the clock. If that clock is running, that decides the speed of the processor. So if that is running, the power is actually required. So if you turn off that clock, we can actually reduce the power or energy requirement for. If we reduce the energy requirement for that, we can reduce the power requirement also. So we can save the energy and dynamic power. For example, if no FP instructions are executing, so in our processor architecture we have seen that for FP floating point operations we are having separate FP processors available, floating point unit available, separate floating point unit available. If no floating point instructions are currently running, just switch off the clock of FP unit, so that we can save the energy for doing that operation, and also we can save the power requirement that is happening dynamically within the processor. So we are not doing anything extra on this, just switch on, just like what we are doing in our house. We will switch off all the power supply that we are not using, so that we can save the power. Okay, so next point is another method is dynamic voltage frequency scaling. Dynamic voltage frequency scaling, which is shortly called as DVFS, dynamic voltage frequency scaling. Okay, so just look at this, is a slight variation of the previous one, but we are doing something over here. Devices have periods of low activity, so we are not considering about inactive modules. So some devices have periods of low activity where there is no need to operate at the highest clock frequency. So some of the modules are very slowly active within the processor. Very slowly, low active means not frequently active. So for that devices, we don't need to operate at the highest clock frequency. So they can reduce the clock speed of those area where the devices are very low active. Okay, and voltages. So that doesn't require that much frequency, highest clock frequency and voltage requirements, so that can be reduced. So we are having many modern microprocessors typically offer a few clock frequencies and voltages in which to operate that use low power and energy. So whichever devices that uses low power and energy, for that automatically the processor is having the provision of usage of fewer clock frequencies and voltages. So automatically that system will, so it is called as dynamic voltage frequency scaling. So for low active area, reduce the speed of clock, and for highly active area, increase the speed of clock rate. So we are actually reducing the power requirement, because for slow or low active area where we are only giving very few, means very low clock frequency, and we are giving only very low voltages, so that we can save the dynamic power and energy of the entire processor. Then third one is design for typical case, for special type of computer devices. So here we are considering mobile phones, that is PMDs, or we are considering laptops, because all these are handheld devices. We can easily take the device from one location to another location. What is the feature of these two devices for mobile phone and laptop? It won't be working all the time. So whenever we are trying to make a call, whenever we are using the internet, that time only the mobile phone will be active. So often these devices are idle. Okay, mobile phones, every time if you are not using phone, if you are not using net or calling or messaging, so that situation the entire system remains idle, and the memory as well as storage, all these actually requires only less energy. They are actually requiring only low power modes. That is why it is saving energy. Okay, so for mobile phones and laptops, most of the time the devices are idle. So accordingly, as we know, we are charging the mobile phone, and it is lasting for more time, maybe more than 1 day, 1 or 2 days. That charge will be lasting only because of most of the time the devices are sitting idle. So it requires only a very low power. We are not always utilizing the memory, even RAM memory or secondary memory, and for all these it actually requires only less power and energy. Now for example, the dynamic RAMs that is used in these devices have a series of increasingly lower power modes to extend battery life in the mobile devices and laptops. It is having lower power modes. As we know, we can power mode can be set to means like for saving the energy, we can use various power modes. If we set the power mode within the mobile phone, we can save the energy, we can save the power requirement for that. So many of the mobile phones are having the provision for setting these points, that is for reducing the power requirement for that particular system. So all these are, so 1, 2 and 3, all these three are, we are having one more method. These are the different techniques that are being adopted by various computer systems that are being generated newly for saving the power and energy requirement of that particular system. Now the fourth method is called as overclocking. That is the opposite of the previous second dynamic scaling. That is called as turbo mode. Overclocking, which is also called as turbo mode. The chip decides that it is safe to run at a higher clock rate for a short time for only few cores. Okay, so whenever that processor is working on some crucial operations, that time only just increase the speed of clock rate. So automatically it should increase the clock speed. So whenever it is doing some crucial operation. Until, so what happens if we increase the clock rate or clock speed? Automatically more power will be taken and automatically it will raise the temperature. So up to that temperature rise, what we can do is just increase the speed of the clock rate, or that is called as overclocking. So that will happen only when we are working on a crucial operation, some major operation. That situation, just increase the clock speed. We were considering about flat clock rates, but here we are considering overclocking for some special task up to some point. That means up to the level of the maximum temperature that it can hold. Up to that it can increase the clock speed, then reduce the clock speed when the temperature reaches a particular level. So for example for a single threaded code, if you are having only one thread that is to be executed, the microprocessor can turn off all cores and run only one with a higher clock rate. So assume that if you are having 10 threads available, for the different 10 threads we need to have the clock speed, that clock rate to be maintained for all the 10 threads. But now if we are having only one thread that is being executed at the same time, we need to give a higher clock rate for that single thread alone. All other threads are actually not active now, so give a higher clock rate for the, so that we can very fastly complete the task and we can come back to the normal clock speed. And all other clock rate, for all other operation, the clock rate will be reduced to some smaller range only. So overclocking is also another mechanism that can be adopted, or that is being adopted by many of the microprocessors to control the power requirement and power usage of the processor that is used within the computer system. So these four are the different techniques to improve energy efficiency despite the normal flat clock rates and the constant power supply available with that, the voltage available with that particular processor. Now the processor is just, so we are again considering energy and power, one more point related to microprocessor, energy and power within a microprocessor. The microprocessor is just a portion of the whole energy cost of a system. So we are not only consider, so the major cost element is processor. It is when we consider the entire computer system, this processor is only a portion of the whole energy cost of a system. For other devices other than the processor, all other devices, all other simple elements also require energy, and for that also we require more power. But why we are considering processor is the major part of a computer system that actually uses, where we actually require the clock rate and the speed improvements and the major processing of a particular task. So it is only considered as only a portion of the entire system, but still it is the critical part of the computer system. So it makes sense to use a faster, so we are having a proposal generally given like, it makes sense to use a faster, less energy, that uses less energy efficient processor to allow the rest of the system to go into a sleep mode. So every time when a designer tries to develop a new processor, he need to go for a faster system that will execute with more speed, that uses less energy, that is efficient due to the usage of less energy, to allow the rest of the system to go into a sleep mode. So whenever the processor is active for some operation, it makes the other part of the system into an idle or sleep mode. So that is the, so processor is there, so this is only one portion of a system. Other devices are also there, but when processor is active, when it is working currently, it is doing some crucial task, all other part of the system, the computer system, that is to be made into a sleep mode and give the chance to only the processor. So this strategy is called as raise to hold. Raise to hold, that means we are giving an importance to the processor alone by keeping other part of the system into sleep mode. So that is also a mechanism for, or which is the, what you say, as processor is a major element or part of a computer system, we should give importance to the processor. We are considering the speed of the system itself by looking at the speed of the processor, clock rate required for a particular processor. So it will be given importance, and all other part of the system need to be set idle so that we can give importance to the processor whenever requires. And if we follow that strategy, it will be a better choice of creating a new processor, and this strategy is usually called as raise to hold, which is one of the major strategy used with many of the processors that are used in the newly created computer systems. So that is all about the energy and power points, energy and power related informations that is part of a microprocessor. So last session we were discussing about power and energy in a general system perspective, but today's session we were discussing about energy and power, especially for the processor, that utilize more power and energy when compared to other part of the computer system. I hope the portion is clear. We are not in a very detailed description on these topics. We are only giving an awareness of the major designer point of view. From the designer point, we are discussing only about some points to be considered when they are trying to design a new computer system. As we were describing first, like the design of instruction set architecture, then hardware trends. Within the hardware trends, we were discussing about integrated circuits. Now within the integrated circuits, processor is the major IC that is used. Now how we can, in the IC itself, power and energy is the major element. They are the major elements. So how we can control the power and energy required and needed for the processor, and how we can manage the controlling of these two by using various mechanisms. Thank you.